Great. So again, welcome to all of you
Ciao,
to this citiwatts e-learning session module 2. And today what we're going to have in the next 3 hours is heat planning, toolchain and district cooling. My name is Markus Hummel. I work for eThink Energy Research located in Vienna. So let's go into the slides. So as you are aware, most probably this is module 2 now, out of in total 7 modules that that are included in this e-learning 2025 on the citiwatts platform. We had an introduction last Friday, 1 hour into the platform. Now today is the longest block, 3 hours on the heat planning, toolchain and district cooling. Then Friday this week, Thursday this week, there will be a Q&A session on the heat planning toolchain. So if you have questions in working with the different modules that we are going to present to you today, you have the opportunity to get feedback, to get questions answered this Thursday. On Friday, then there will be a session on electric vehicle mobility. 8th April, then we have a session on flexibility, system flexibility in a simplified energy system analysis tool that is linked to the citiwatts platform. Then 10th April, all modules. And on May 16th, so in another month, there is another Q&A session, English and German. So if you have questions after that from the work you did.
Markus, there still seem to be some connectivity issues with your connection. So can you maybe put off your camera? Maybe that helps.
Yes, let's do so. If it still persists, I can also try to change the network still. Yeah, so give me a hint. Thanks a lot, Max. Good. Yes, so today we're going to dive into this second module, so the heat planning, toolchain and district cooling. What is awaiting you in those next 3 hours? We're going to start setting up scenarios, workflows, tool chains, and the use of the scenario assessment spreadsheets. That's going to be presented by Max right after my welcome is finished. Then we're going to have a slot on gross flow area, heat demand, and future projections. We're also going to have an exercise on that, demand data and projection, that will be presented by myself. Then we're going into, so after those demand data and demand projection that we use as a basis, then we go into district heating potentials. We have a basic module that will be introduced first, and then an advanced module. Both of them will be presented by Mustafa. And then we are going into the district heating supply options, again with an exercise presented by Ali. And then we switch from heating to cooling to district cooling, including an exercise presented by Adit. In between, around 2 p.m., going to have a 10 minutes break. Yeah, with that here, you see the team of today, or in general, the organizational team of the e-learning up here. Max, that you already know, Eva, me, myself, Mustafa, Charlotte, and Midiana, that organized the training. And we are also going to have today Ali in the team and Adit Mala in the team, both from TU Wien, that developed or further developed some of the modules, those that they are going to show you. Good, with that short introduction still, you have all or that have been in the training on Friday in the first session already know that, but still, as it is very important, a quick rush through that introduction again today. So citiwatts actually is a further development of hot maps, and what we did actually is to adjust core calculation modules, new modules in different fields as well, and we try to improve usability and user experience in order to come to TRL 8. Platform, standalone tools, wiki, and as you can see here, an overview of all the options that we have, all the calculation modules. And here again, notes in the platform so that you have it in the material. You will receive those slides, and so that you have it in the material by hand. And very important, if you still didn't do so, please do so. You will need to have your own user in order to be able to work with the different options and the different modules that we're going to show today. Yeah, and with that, I would like to hand over to you, Max. Give you the floor.
Yes, thank you very much, Markus, and welcome everyone. I'm presenting on the toolchain, as said, the workflow, how to apply the toolbox basically, or the citiwatts tool for district heating investigations. Yeah, I already presented this briefly in the introductory webinar, but we're going to elaborate that further on today. So the whole thought of this is as said, that the toolbox on citiwatts, the maps, it consists of very many different aspects that can solve a lot of different analysis for your area that you want to investigate. But the value of it comes when you actually chain these together and then use the output of some of these as input for the others, and then chain a full scenario analysis. So we did not develop a tool that, like, by one or two clicks or one or two small steps gives you a full energy system analysis. It's really this component-based approach to energy system modeling, in this case district heating modeling or heat planning. So that's by intention, you could say. That's why it looks like this. And what we then also have decided is to not have, for instance, individual heating, which would be the reference for many places, the reference technology for heating supply. That is not included as such in the toolbox, so that's also something that we cover on the side, which is actually what I will focus on in this presentation now. To guide you through this slide and the thought behind it in more details, well, the overall goal is to develop scenarios for the heating supply of an area. And in this case, we are still doing this on a rather screening level. That is something to be aware of in the way that we use this tool. So you can also use many of the components of the tool. So many of these calculation modules, as we call them, CMs, you can use for very detailed analysis also. But the approach that we're presenting here in this toolchain is the rather screening level approach. So if you want to start by getting the picture of how far out do we think it's reasonable to develop district heating and how much will be left for individual heating, those kinds of analysis. So you can also investigate some sectors. So for instance, dive into the district heating supply options, but in the toolchain we present here, it's going to be on a more overall level. In order to assess the scenarios for the heating supply, you want to have a picture of both the individual heating and the district heating potentials on the side. And to start with the district heating possibilities, what you want to have is a picture of where your development or where your heating demand is developing, and your building mass, your gross floor areas, your building volume for that matter, but the buildings that are there, the information about that. And that you can do in multiple ways. You can start by, you will obviously have some kind of data to begin with. We use the default data that is in the toolbox today for the reference that we're calculating here. But if you have your own data, they would of course be appreciated, that you can, like this, use your bottom-up data. If you have better data than what we get from registers and so on, then feel free to use that. The concept behind getting this future picture of the heat demand in the area will be similar though, because what it's all about is that if you have nothing else, you can start with some default data, and then you can simply apply a scaling factor to then for instance, scale it to 70% of the current data, or what it may be reasonable for you, and then you have a future picture. So you can just take the entire area that you have and then scale every cell in that raster grid to a lower unit. And like this, you would have a scaled output of some input data. You can also go a more advanced way in this, which is what we call the CM demand projection. It's built into the tool, and we're going to demonstrate them both actually. But for the very need of the exercises, you can stick to just simply applying a scaling factor and then have a future picture. But you can also do the advanced one up here, like I said, and that will also give you a development of the gross floor area in the area and the heat demand development for those years that you specify. And we're going to demonstrate those later on in the exercises. What we need this for is then to assess what we think is reasonable for the district heating potential areas. So in what areas do we think it's reasonable and feasible to develop district heating? And there's a calculation module for that, and that will then, in consequence, give us an amount of heat that is to be covered by district heating, so to be supplied by a grid-based solution. Again, we're going to dive into the details of how to apply these calculation modules throughout the day today. This is just the overall concept to it. Also, and that's maybe a little bit reverse now, but you can also, to qualify your areas that you look into, you can start by a rough assessment. So that's what we call the basic functionalities about district heating potential areas. That is the first step that most of us are going to present in a second, and then you can always dive deeper and go into the economic assessment calculation module, which is more advanced. What this will give you is, like I say, it's going to give you the amount of heat that is to be supplied by district heating. What it doesn't get you is the heat loss, for instance, and that's something that we then have in a spreadsheet on the side. So here we as a part of the team in the project, we try to give you a framework that you can use as a template for your own analysis. And yeah, like said also already in the introduction section, we will work for the city of Offenbach in Germany, and there's prepared some inputs for this. So here you can see how we calculate from those outputs from here for this calculation module, and then find out how much heat is to be put into the grid, because you will also have grid losses on top, of course. That will then give you, in consequence, you will know how many megawatt hours, you could say, how much energy you want to put into a grid. But it doesn't tell you how to supply this district heating. So how to supply, how to create all that heat. And therefore there is a calculation module called the district heating supply. Where you can again just use it as it is, and then you have some data, but you can also go into more advanced analysis in it. So you can use the potentials that are within the toolbox. We already presented those in the last introductory section. But if you have better local bottom-up data, in this case for Offenbach, you most likely won't. But if it is for your area, you may have better information about the forest residues, whatnot. So please feel free to use those instead. And then you can create scenarios in the supply CM. As there are many input factors into this, you will see that later today. We also have made it possible to create consistent inputs. So you can upload a file and then have the same inputs every time you run the scenario, or you want to change just one of the parameters and so on. We have tried to give you an overlay to make it easier to adapt these things and then still have consistent scenarios. So if you want to cover, for instance, different district heating shares, which you may have found in the analysis up here, then down here you can make it more easy to apply those and evaluate those. Yeah. Everything that is colored, like in this, I would call it citiwatts petrol color kind of scheme, is something that is in the toolbox. So that's on the platform that was demonstrated last Friday. Everything that's greenish is in Excel, so that's something on the side. And then we have also the red for PowerPoint, where you have the this presentation, which you will get access to after the webinar today, and to read the exercises that we have prepared. But we also have created a PowerPoint template which you can use for documentation. So there's also more elaborated exercises, a little more guides on what is already presented in this presentation. It's elaborated a bit, but it's also a format that you can just paste your results into in order to have some documentation for what you've been doing. One final remark is sorry about the scenario assessment spreadsheet, is that we have a tab for decentral inputs, and this is because the approach in the heat planning aspects and in citiwatts is that if you want to develop district heating, you must, of course, we say of course at least, be compatible economically with the alternatives. If you're more expensive with district heating, people most likely won't want to be connected, and even though you may be able to force them by law, that may not, or that won't be the good process to get a heat supply that should be based on agreements. So that's why we're also focusing on the individual heating here, even though the scope of the calculation modules is small in this system. Yeah, said in a slightly different way. I already presented this kind of, but we have some PowerPoints. So this slideshow with the exercises and then the template on the side. You also are to work in the browser to use the tool itself, and we'll explain what buttons to click when, basically later today in the session. And then we have the scenario assessment spreadsheet, which I will present in more details in a second, where you can click around as much as you want. And all these are going to be made available on the Google Classroom just after this webinar today. And then there's also this input generator, which Ali Cook from TU Vienna will present later today. So first things first, with the scenario assessment, as said, we want to find the reference. We want to know what level of costs is reasonable to reach, or which may be our target for the district heating system to at least reach, and hopefully less than this. And the general rule is, as we presented, is that and that's just put the same thing that I just said into a mathematical formula, basically, is that if the cost of the decentral heat supply is lower than the cost of district heating supply, people will not choose district heating, and hence we have coherent areas with individual heating supply. However, if the cost of decentral heat supply is higher than that of district heating, then people are more likely to connect to district heating. For this, we need to aggregate the buildings in an area into some categories of buildings in the way that we have created this scenario assessment spreadsheet. And we have stated some shares of kind of buildings. So we according to the calculation modules, we need to specify multifamily houses not renovated, same for renovated, and then single family houses renovated, not renovated. And we assessed some shares for you for the case that we're calculating. If you are to apply the same spreadsheet for your area, then please make sure that you adapt these factors if you don't think that they fit the city that you are looking at. And we don't have a full register of these kind of data. This is something that is very hard to get many places. We know that, but this is our assessment for the case that we're calculating here in Offenbach. Yeah, and what we also need these for is said here in the beginning, it's to simply have a more detailed picture on what kind of, for instance, if you calculate the reference price for a heat pump, it's rather interesting to check what effect you will have to be able to, what power you need to supply the heat in a given building, and hence it's not irrelevant which kind of building you're looking at. That's one of the most important takeaways. Also, different size buildings have different size of full load hours for the unit that is being applied. But we'll look into that in a second. Yeah, when you're using the scenario assessment Excel tool, to a high extent, we're working with export data from the toolbox, and the colleagues will later today show you some of the examples of what to copy out, where to paste it, and so on. But one very important step to note here, and I already said that last Friday, but here I'm going to repeated and also showed in a second, is that you make sure that the decimal separator should be dot, and then your thousand separator should be comma. So vice versa to most of the Western European ways to spell it. Yeah, you can also by hand adjust it, but the easiest way would definitely be to change it in Excel. I will show you in a second how to do that. This is how it looks in the window I'm showing in a second. However, my window speaks Danish right now, so this is why we have the screenshot here, but this is the steps in the files, in the settings that I'm going to adjust in a second. If all that doesn't work and doesn't help you, and it still speaks comma and dot instead of dot and comma, you can also adjust it in the country settings and the language settings of your Windows installation. However, that should not be necessary. It isn't on most machines, as we see. But here would be the link again, speaking Danish, sorry for that, but that's all my Windows knows. So yeah, feel free to reach out to us if you have issues with using the dot comma. Yeah, that being said, I dive into the spreadsheet instead. And again, it will be made available to you right after the webinar today. We're starting with the content tab, which basically is the information about the spreadsheet. You know this from many other tools, I'm sure. One thing that I want to highlight is that we have a color coding. So across all tabs, we use the same coding. So data that you're going to feed into the toolbox, basically, or to document what you have fed into a certain modeling run or whatnot. We have this turquoise background. The yellow would be outputs from the toolbox. Green is default data that we have selected as the team behind, which you can then discuss and adapt if you don't agree with us. There's also one kind that you can copy to another spreadsheet, and blue is generally instructions, and gray is calculations. It will explain itself, I hope so, at least when we go through it, but just to know that we work with this consistent background coloring. Before just moving on, I'll just quickly demonstrate this dot comma that I promised. So under files, in this case Fila in Danish, you have the settings down in the bottom. And then under advanced, you have, it will say something like use system separators, or yeah, it will say in your language, basically, mine has been already shut off because I already have it in dot comma instead of comma dot. If I would just do this, it would be vice versa. So now I would have comma as decimal separator, and now I have dots as decimal separator. That's all it takes, and then you can do that without restart and so on. Moving on in this spreadsheet, we also have a little list of references. That's not that relevant. I will explain the one reference that we're highlighting here. Coming to our first tab with data, that would be our decentral supply inputs. Again, we want to calculate the reference price for heating basically to find out what level of cost is reasonable to use. To want to reach, and Mustafa Falenjat will show you later today in the economic assessment for district heating how we then apply this. I mean, like this, it's basically built like any other spreadsheet. I would want to say we have a matrix constellation of parameters down here, and then categories of buildings over here, and then the crossing of those would be the data point that you want to investigate. So for instance, your specific useful energy demand is assumed for multifamily houses renovated. We put it 100 kilowatt hours. Over here with the comment, we say where it stems from, and it can either be an assumption. It can also be an assumption documented by one of our partners. But then many of the cost factors and efficiency factors come because we work in Germany. We have a technical data catalog from the it's a competence forum for municipal heat planning under the Energy Agency. Yeah, and it's prepared for heat planning. Again, if you have better data locally, please feel free to use those. But this would be a standard reference to use for heat planning in Germany. Denmark has a very similar catalog, as you may know. Well, the factors that we calculate for the different heat installations is of course the energy efficiency and the economy. So overall, we work with an energy carrier, the price for that. We work with the efficiency of the heating system. We work with the lifetime, so over how much time you want to depreciate the cost of a certain unit. We work with a specific investment, giving us a total investment in absolute costs, and then also the operational costs. That being said, this is just the calculations. So here we have, with the green background, as I said, we have all the assumptions and all the calculations that go, or the figures that go into the calculations. Please feel free to have a look at them, and please keep in mind that we are working in a German context here. But yeah, I hope that you will find them interesting and useful. The way that we use this is that we then, based on these input parameters, calculate lifetime cost of heat for the different technologies to find that reference price. Which reminds me that I forgot one part earlier, sorry, but we calculate in general with a basic scenario, and then we have a high energy price scenario on the side. So there's already a sensitivity analysis built in. So if we go back to the tab before, sorry for that confusion. Over here we also have the high energy price scenarios, where we simply have adapted the energy carriers prices slightly. And then if you want to see more extreme differences, of course you can feel free to adapt those figures more, that they will vary more. However, then you can't use us as the reference anymore. But yeah, this gives us a level of cost that we take as the part of decision making, and it's very important to keep in mind that what we say that is the best way to calculate for heat planning is to work with levelized costs, and we also take the capex into consideration. So we depreciate the investments over time to have a full cost picture of it. What this basically shows me right now is that I have a reference price of somewhere around 150 euros a megawatt hour, or 15 cents for the kilowatt hour, as some are more accustomed to present it on. And yeah, given the different technologies that we have selected here as a reference, the biomass automatic boiler, the air-to-water heat pump, the brine-to-water heat pump, or the direct electric heater, which is actually not used for some of the building types. Primarily, it's not used for the multifamily houses. It will show you a very different way that how much your cost is depending on the energy carrier. Of course, for electric heating, quite much. Whereas for the heat pump, the energy carrier will not be that much of an amount. However, the investment in the heat pump will make a bigger part of it. However, the overall level of these 150 to 180 something, that's kind of your price to beat. This is basically the takeaway that we want to help you finding quite soon, because then we can jump easier into the calculations of the district heating alternatives. Then you can also find some CO2 information and so on, and the absolute capital costs for the investments that we're looking at. So what level of upfront investment do we look into? And in the bottom, we also have basically taken the same analysis, but then broken it down. Instead of into the megawatt hour, we look at it into the square meter, because for some heat plants, they prefer to look at it at the square meter. Yeah, that's simply to give you a little bit of different things to evaluate on, and then to quicker come into the discussions of these parameters when doing heat planning. That's basically our take on this. Just a slight remark on the end. We will jump into these parts of the spreadsheet later today when we look into the other into the other calculation modules. So for this, it's the economic assessment CM. As said, with the turquoise background, these would be things that you have entered into the tool. So on the Wiki citiwatts platform, this is the figures that you typed in there. Whereas the yellow would be the export from it. And we have here pre-filled it, pre-populated it with a little series of modeling runs, just to be able to show you what this then does once you have filled it out. You don't need to fill it from end to end, and Mustafa, like I said, he will present it later today. Same goes for the supply. So this is when we know how much district heating we want to develop. We have basically the same setup for the next CM, which is the supply option. So here we look into what kind of units will supply the heat for district heating. Long story short, you paste all these figures in, and then we have in the bottom prepared some analysis on top of it, some calculations which you can check out and see if you agree or disagree with our assumptions on for instance, what will be the margin for a grid operator, or what will be the electricity consumption and costs for pumping and circulating that district heating, those kind of cost factors we put on top because it's not in the calculation modules. Long story short, we get a comparison of those scenarios. So that's why I pre-populated some of these scenario runs to be able to show you these figures. Is that with the different scenarios, I get different district heating amounts, obviously some energy in some scenarios based on those assumptions applied, of course, more and some less. My CO2 emissions are rather stable. However, I also only calculate in the same park of of production, so it's rather CO2 neutral, little intense. And then again, all the way down, you get more and more detailed. What I want to highlight is that we have tried to create, I would say, something as close to a full cost analysis on district heating as possible. So here we have just very similar to the one that we had earlier. Per megawatt hour, that is, split the different cost components from the different calculation modules. You will get there later today, basically, when you follow all the steps that we present. You get the different cost components of the district heating. And again, the takeaway is basically, as earlier we said, we were in that range of 100 to 180, 150 to 180 euros per megawatt hour. Here we reach something closer to 110, 120. So we're basically, with these analysis, we're in a range where it makes sense to discuss district heating. If we were far off or more expensive than the individual alternatives, there would be not much reason to look into it more. But here we already can now see this is kind of the level where it makes sense. Just a little final remark here is that we have this selection that you can choose the down here for this showing with the square meters at least. What kind of building are we looking at? Because then the price will vary whether you have a large heat pump in the basement or if you have one heat pump per building. And like said, later today we're going to dive into the inputs from the other scenarios, from the other calculation modules. Sorry, but the reference is the individual heating.
Great, thanks a lot, Max. That was a quick and good introduction into our scenario assessment and the whole tool chain. If you have any questions, you are always free to paste them into the chat, and we're going to pick them up later. Now we go into this first part of the tool chain. I'm going to share my screen again. I hope my internet is better right now. I switched to a different WLAN, so I hope, please indicate again, Max, if we have any issues. I hope not. Good, so you have seen the whole overview, and now we are going to dive into this first part. Hoppala, let's go. So again, just as a starting point for you, the reference, this tool chain. And now for the next 20 minutes, we're going to dive in this top left segment here. So heat demand and gross flow area density maps reflecting the current situation plus a potential future situation. And here, let's start with the current situation. So we want as a goal to see a map of the heat demand and of the gross flow area, and where is more heat demand to be expected and where is less heat demand to be expected. And with citiwatts, we have now 3 options to analyze here, depending on the time you have available, but also the data that you have available. First option, default data. So we have heat demand and gross flow area density maps in the platform for entire EU, and you can use them and very quickly come into analysis using those data. Of course, they are rough estimates, and you should always check how credible they are for your exact location that you analyze. And in general, as I put it on a note here down, is you should use as much local data as possible. So, but in order to come quickly into some analysis, you can use this default data. A second option that you have is, imagine the situation you know how much heat demand how much heat is demanded in the entire area you analyze, but you don't exactly know where. So you did never do an analysis of where are the buildings, where are more buildings, where do more people live, where is more activity. So what you can do then is you can simply scale those maps by a certain factor. So you can have a look, okay, how much is the total heat demand in that default data, and you can scale then those maps to the values that you know. So that's number two. And then we have number three. Number three is you can use your own data. So if you have estimates of the heat demand and the gross floor area in the buildings in the area, you can use that and you can generate your own heat demand and gross floor area density maps using the calculation module, customized heat and gross floor area density maps. And as I said, depending on the time you have and the data you have and the goal of the analysis. Let's go into this first option, so just that you understand the data that are in the platform. In general, they are generated based on national data at first, and then broken down to the hectare level. Starting with the gross floor area, so based on population data sets, Gallego data set, and human settlement map, plus also the footprint map, we derived those areas where we have footprints and those areas where we might not have footprints. And in order to come to the volumes, because this is not available, not a map of the building volumes in each of those areas, we did that based on an estimate of around 150 selected cities where we had those relations. So we derived a relation of the building footprint and the number of floors. All of that, all the methodology, all the data is described in a paper that you can find here and can have a more detailed look into that. Here you also see then for the heat demand, how we did it. So we started at the NUTS 0, so the national level, then broke it down to the NUTS 3 level, still using indicators like number of buildings, number of dwellings, share per construction period. So that data is still available on that NUTS 3 level. And then we further broke it down based on other proxies like population, like land use, or also value added. But as I said, more details are given in that paper. I won't go into detail. You can also find in that paper a comparison of that top-down approach with bottom-up approach. So for selected areas, so based on really the buildings and the data for the buildings that we had available in some selected areas, and you can see where deviations arise. So that's the current state. Then how do you go into the future? Of course, heat demand and gross floor areas might change. Again, here we have three options to offer in the platform. First of all, a simplified approach. So it's basically the same approach as I showed for the current situation, approach number 2. So what you can do is you can simply take the heat demand and gross floor area density maps and scale them according to what is your expectation of how demand evolves. So that's the first one and the most simple one. Second option that you have, there is a calculation module called demand projection. I will show it in some minutes. So what you can do here is, or what the module does is, it takes the default data, the default maps, and it takes reference scenarios that we have calculated for all EU countries, and it scales, or it actually adjusts the default data to fit to these reference scenarios. that we have calculated. The reference scenarios were calculated at the national level. And what you can do is then, I mean, you can select out of different of those reference scenarios, and you can again then adjust some of the parameters in those reference scenarios in order to fit your expectations. And number 3, again, you can use your own data, so you can integrate assumptions for different typical buildings, regarding renovations, also regarding new developments, regarding demolition in your own data set. And again, using this customized heat and cross flow area density maps module, generate new maps. Yeah, so you are free to choose here for the training what you use. We suggest to start with the simple one and then become more advanced one after the other. But you're, as I said, free to use whatever. I will show it also to you, but we also highlight here, there is an important distinction in the platform between a layer that is a heat density total right now, so more or less, reflecting current situation, and the heat demand density future. This is important because in one of the calculation modules that we will see later, it's important that the tool knows which is which layer. So you need to be aware to upload it as a future layer. But I will show it to you in a minute. Yeah, so here it is again shown so that you have it in your slides as well to refer to it later when you do it. I will show that to you as well. So you will download it and upload it as a future heat demand density layer. Coming to the exercise, in general, Max had also mentioned it already. The idea, what we have prepared also for you is an exercise for a certain city. Why did we do that for a certain city? The reason is that we prepared a set of input parameters, especially for the district heating supply model. Why? Because so that you have a set of data that you can already use. Of course, you are free to calculate whatever location you want, but then you need to take care to adapt the data in the different modules, and especially for the district heating supply model. This needs a little bit more time to do so. So we have prepared data for Germany, for the city of Offenbach am Main, so you can follow that city. That's primary suggestion, so that you have all the data without the need to adjust a lot. You can directly dive into that. I will do so also when I show now parts in the tool. And then you go through the different points here. I will not go through it in detail right now. It's actually what I have explained before. So you go to the location, you have a look at the map, you have a look at the indicators, and then you try to set up a map for a future situation. Yes, and with that, I go into another PowerPoint that you will have available. It might help you to collect results. So as Max has already said, we are going to provide you an Excel file, this Excel file that Max has shown just, where you combine calculations from the different modules, and you see as results then some figures on costs, and you can compare the costs of decentral supply with the costs of district heating supply. Here is another means for you to be able to collect results, not only quantitative results, but also qualitative results. It's with the idea to compare those data for decentral supply and data for district heating supply. And you have, for the exercises that you will find later, the option to make your notes, to insert screenshots, and to insert then also results from the scenario assessment Excel file. The idea behind is imagine you analyze that location and you want to present the results later to stakeholders or city administratives or anyone who is interested. Yes, and with that said, I'm going to go into the platform right now. Yeah, as we have shown, so citiwatts.eu, you can reach the platform. Let's go to the app, and I will directly, I'm still in, yes. Let's go out and go in again so that you see it's important to log in at the beginning. And then I go here now to the city of Offenbach, so you can search that here. What it gives me now is Offenbach am Main in Hessen. So that's the city that we analyze. I will select Lao 2 level, as we have heard last week. So that's the municipality level in many of the European countries. I select it right now. So that's the analysis that we are going, that's the analysis area. Important, I repeat that, has been said as well, but it's important to select the region in order to be able to use any of the calculation modules. I will show it to you now. All of them, or many of them, are accessible. If I don't select it, I'm not able to run any calculation. Good. With that, so as we've seen last week, so we have quite some layers that we can have a look at or that we can show. At the moment, we're going to focus on the buildings layers. So the rest I'm gonna put away now for the moment. And here in the building section, you will find that default data that I have mentioned in the presentation before, and it's heat density total. It's separated actually into heat residential sector and heat non-residential sector. So as you can see, it's the residential buildings, but also the non-residential buildings, and this does not include industry buildings and not the process demand. Besides the heat demand, you have also the gross floor areas, again split, well, whether total, so in that total you have the total amount, all the gross floor area, but you can also see it separated between residential and non-residential. What you also have is building volumes, not going into detail right now. And what you also have is a split of that gross floor areas, so share of gross floor areas in different construction periods. And we have we did that for 4 construction periods. So before 1975, between 75 and 90, between 90 and 2000, and between 2000 and 2014. And that is important also to understand later the demand projection module. Now we've selected them. We see them on the map. They are all overlaying. Now go back to the tools section, and now we can load the results for those layers that we have selected. And you see that now here on the right side in the results section. And for each layer that you have selected, you see the indicators here. So in total, we have roughly 1 terawatt hour of heat demand in that area. It's 63, well, more than 60% residential and less in non-residential buildings. And we have in total around 7.5 million square meters gross floor area. And here you see again the split. Good. Now, so that's the default data that we have in the platform. Now, first, this is actually first option that you have, so you can simply take that data. Second option that you have is you can adjust that. So if you, for example, know, well, that's not, I know we only have 700 gigawatt hours in that area. So what you can do is you can apply a factor and scale that heat demand density map down. So where can you do that? You go to the calculation modules, and here in the demand section, you have this scale heat and cool density maps. And here you can, it's a very simple module, and you can simply use a relative factor, run the module, and then the module generates another layer. You cannot see it right now because they are all overlaying, but if you scroll down here on the right side, you see there is a new layer that's as an output from the scale heat and cool density maps. It was generated right now. So 135550. And as you can see, it's now 687.69 gigawatt hours in total in that map, which should be exactly 70% of that value. So now you have a map that has a lower demand, because you might know that this is the lower demand. So that's the second option that you have. And the third option that you have is, again, a calculation module. So using your own data. And you find that module on the bottom here in the section standalone CMs. What does it mean? It means it's not integrated in the platform. It's actually a Python code in a package that you can download. You can go here to the repository URL. You click here, and here you have the repository. You can download it, and then you can run it. You have the README here with all the instructions. And just that you have a picture of what it would mean is, it's actually what you need to provide to the module is a simple CSV file looking like that, where you have rows. Each row represents a demand point, and you can have, so it's point data actually that you generate. You need to give an X and a Y coordinate in the 30-35 projection, and you give a demand value, and you give a gross floor area value, and you give a construction year. That's it actually, based on the data that you have. You need to simplify it in order to receive such a file. With that file, you can go into the Python code, click on run, and you get heat demand density and gross floor area density maps that you can directly upload into the platform. Good. Let's go back. So now what you can do that I promised you to show is you can go back to the layers section. And if you go down to the bottom, you see here now this map that has been generated. I put away all the other maps right now that we have selected. So what you see is now only that map. And what you can do right now is you can whether download it, that's what we can do now, or we can also already save it as a personal layer. What is now done is it's not downloaded, but it's directly imported into your personal layers. Now it's one of those layers here. Let's see where it is. It should be that one. So it's now directly in the personal layers section. In the personal layers section, it is saved as the same type of layer as it was. It was a layer of heat demand density, current state. So if you want to use now this simplified version or this way to generate a future heat demand layer, like we can also say, okay, we believe heat demand fits like it is right now, but we want for the future status to use that 70% lower demand layer. What you can do is you download it as I did right now. So now I have it in the downloads. I have it now in the downloads. So here it is. That's exactly that layer. And I can now upload it again. I go to files. Here are my files. I upload it. I select it. So that's it. I select it. And now I select the layer type, and here I need now to not use this heat density total type, but I go down, I go down, I go down, and here I have the heat density total future. So now I upload it as a future layer, and now the system knows this is intended to be a future layer. This is important when we come back to the district heating area potentials calculation with the district heating economic assessment module. Yes, and with that, I just very quickly introduce you to the last module of this section, which is the demand projection module. So as I said, you have, if we come to the future status heat demand density maps, we have the simplest way to go is to use the scaling module, adapt the default data, have then a future map. The second one is we use this demand projection module. And what the demand projection module does, as I said, is we have a certain scenario in the background, and it actually we have 4 scenarios here, distinguished mainly regarding renovation rates. 1, 0.5, 1, 2, 3%. And there are assumptions on the depth of the renovation measures for the different types of buildings in the background. And the idea is you choose one where you think this is a reasonable renovation rate, and then you calculate once, you choose then also the target year, and then I will just run the calculation right now so that you see the results. And in the meanwhile, I show you the input data that you can afterwards change. So the idea is you let it run and you see, you have a look at the results, and then you can decide how to adapt them. And what you can change is you can change the reduction of the floor area compared to the reference for the different construction periods. So that's what you do here for the 4 construction periods. Here, what you can do is you can also scale up or down the reduction of the specific energy needs compared to the reference scenario. And that's exactly that depth of the renovation measures that are in the background. So you don't have to go into the detail of each and every building, but you can have a look. So now we see the results of the calculation, and you can have a look at those results and now adapt, scale up and down some factors, like, for example, this area reduction or this specific energy need reduction. You can also change the population growth. So there is a population growth in the background, as you can see here, and you can change that according to your own figures. Yeah, that's basically it from my side. Yeah, with that, you can generate heat demand and gross flow area density maps for the current state and the future state. And with that, I will hand over to you, Mustafa, for going into the district heating analysis modules.
Great. Thank you very much, Markus. Before continuing with the next module, I suggest if you have any question, just type in them in the chat box. All right. Then I share my screen. So I hope you can see now my screen. Just give me a second to arrange everything. Perfect. Good. Now I'm going to introduce you 3 calculation modules, one after the other, starting with a very basic one, which is district heating potential areas user-defined thresholds. That's the name on the platform. It's a simple calculation module that can be used for the orientation to see where it could be potentially interesting for a district heating system. and it is basically focusing on the demand side. So it looks into the demand heat demand densities, and you can use it for the first quick identification of areas that potentially could be interesting for district heating. So the calculation modules basically takes two simple input parameters. One is the minimum heat demand densities in each hectare, and the other one is minimum heat demand in a district heating area. So if you were in the first block that we had on Friday, I show you how a raster layer looks like. Normally, it's a pixel-based data set, so each pixel has a value. And with these two input parameters, we will look if every pixel is fulfilling the first criterion, and then once we have those pixels selected, then we look if any connected areas, like the one I have shown here, if those colored areas fulfill the second criterion. And if this is the case, then it will be shown on the platform. So what can be done basically with this calculation module? As I said, it's based on the demand side. Nothing related to the supply side has been included in this analysis. And also there is no economic indicator or nothing related to district heating grid itself. So it's a simple demand analysis. I jump into the platform to show you how it works. Basically, I go to the city of Offenbach in Germany. Offenbach is a city just very close to Frankfurt, so that you know where it is. Here is Frankfurt and here is Offenbach. I activate the heat density layers to see where are roughly the potential areas. As you can see in the map here, you see the hottest spots, but we will see if all these areas are relevant for our analysis or not. And then I move on to the calculation module tab. Here under district heating and cooling, the first calculation module is district heating potential areas, user-defined thresholds. I select this one. And here we have two input parameters. So depending on the region you're looking at, you may have different indicators. It's being said in literature that minimum threshold of 300 megawatt hour and 1 gigawatt hour could be still interesting for a district heating system. So you can play around with this number if your region is not very densely populated or does not have so much demand. Maybe you will go a little bit lower to see where are interesting points. If it has very high densities, like what we see here in Frankfurt, maybe you decide for higher thresholds to identify or cherry pick the regions. I just run the calculation modules with these default values to see what comes out. It's pretty quick. So as you can see, we will have here some indicators on the total demand inside this identified district heating zones, and how much of total demand is being covered in identified region. As you see, almost everything with these input parameters are included. The reason is that we have one huge area which includes 825 gigawatt hour of demand, and also a smaller one, probably this one is it, or somewhere that I cannot identify right away. This one. So these two regions are identified. So maybe I want to have better overview, then I can of course move on with higher densities, put a higher threshold level to remove pixels that do not fulfill. Yeah, maybe I need to refresh. All right. So now I give 500 and run the calculation module once again. So it's a little bit smaller now. So some other regions are removed, and now we have 3 regions in the map. So you can play around with these numbers to identify potential district heating areas. And there are also some charts provided. You have like KPIs on every single identified coherent area, and also the annual demand compared to the demand inside coherent areas. On top, there are also some layers generated by these calculation modules. You have the option to download them. There are in raster format and also in shapefile. So if you want to work around independently of work with the output data independently of the platform, you have the option to download these layers and see where are potential district heating areas. That's basically the first calculation module. It's a simple one, as I mentioned. It does not, therefore, have so much complexity, and as a result, there is no exercise for it.
Great. Thanks, Mustafa. I think we said that we are going to have a short break right now in order to be on it afterwards. So we have now a good hour and a bit that we had, and we want to drive through the rest afterwards. So that's why we said we're going to have 5 to 10 minutes of break right now. Let's do that. Let's everyone pick up something to drink, go to the toilet, whatever you want. In the meanwhile, we're going to start off again at 2:20, so in 7 minutes.
Perfect.
Yeah, great.
All right.
Thanks, Mustafa.
Thank you.
See you in some minutes.
Sure.
Perfect. Hi, Mustafa. Great. I hope all of you are back. I would say let's just go on. Yeah, as I said, as we've said, if you have any questions, just paste them into the chat. We will have a session at the end, a slot at the end where we can discuss one or the other question. And yeah, of course, we have the Q&A sessions as announced also later this week and 2 weeks and later. But if you have already burning questions, just put them. Mustafa, floor is yours.
Thank you, Markus. So now I continue with the second calculation modules related to district heating potentials. It's based on economic assessment. So what to expect from this calculation module? Basically, it determination of district heating. It calculates the district heating potentials. It does economic viability analysis to see how if the demands change over a period of time, and also if the district heating grid expands over the period of time, then where could be suitable for district heating system, which areas fulfill the requirements provided as input parameters to the calculation module. So basically, it also identifies the suitable areas. Outputs are GIS layers. They show extent of district heating areas. It is possible to see and study the impact of evolution of district heating, connection rates, and heat demands. You can investigate also the cost of distribution grid and house connections, or so-called service pipes. So you get distinguish indicators for these two pipe sets, distribution pipes and service pipes. You get the length, approximate length of them, and also the cost of them per meter, but also per megawatt hour of heat delivered over the lifetime of pipes. And there is another possibility provided by this calculation module, and that is restriction of expansion rate, meaning that you can set a level of expansion, let's say 15 kilometers per year, which is not allowed to be expanded. So if you start building up or construction of heating grids, you say I'm starting from 0 market share, 0 connection rate, and every year I'm allowed to build maximum 15 kilometers. I have certain input parameters that should be considered in this analysis. Find relevant areas for me that fulfill these conditions. Okay, a little bit about the methodology behind this calculation module. Generally, the calculation modules works with raster datasets, heat demand density, and also gross flow area density, or looking to building densities, which provide us the gross flow area. So it would, from these two parameters, the linear two layers linear heat density will be extracted. And there are some set of other parameters, construction cost, constants, and coefficient in euro per meter and euro per square meter, pipe dimensions, and annuity. And from these parameters, I can get the specific pipe costs in euro per meter. Combining these two, or dividing the first one by the second one, I get heat distribution cost, euro per gigajoule or euro per megawatt hour. So all I do is that, based on some interpolation analysis, I look into heat densities and also gross flow area density or plot ratios to see what would be the average pipe dimension required in every pixel of the map. And based on these pipe dimensions that are available and the cost that I have euro per meter, then I can identify the cost. So I have already C1 and C2 here. So this cost constant and coefficient in this line interpolated. And if I have, for example, pipe dimension of 0.15, then I know roughly it costs €1,000 per meter if I use this line. So that's basically the idea. So I have like for every single pixel an average pipe diameter, which would be used to get euro per meter of trench length. How the grid cost is being calculated, it's a simple formula. Basically, I assume that if I want to have an increase of district heating connection rates over a period of time, this will increase, and then from a certain period of time until the end of the lifetime, I have no other modification in the connection rate. So the connection rate or delivered heat remains the same. The calculation module calculates this heat delivery over the lifetime and also calculates the required pipe diameter for these periods and calculates the investment cost. And this formula gives me the grid cost in euro per megawatt hour. The assumption is that if I have, for example, an expansion of the grid, let's say from 15% to 70% over a period of 30 years, all pixels inside the map should follow the same evolution. So it's not like that I have like a starting point and expand around this starting point, but rather it's like a uniform expansion in all places in the map. That's one assumption that we have for this calculation module and should be considered for the analysis. So what are the input parameters that I have here? Basically a set of construction cost parameters for each member state, European member state or member state of European Union. We have provided a default set of cost components, but you have the option to use your own values with the other parameters. I will come to that point. Then you need to provide this first year and last year of investment, which are relevant for saying, okay, the expansion period happens through which time horizon. Then you need to provide the connection rates in the current state and also connection rate that you want to reach. You should also provide one parameter for defining what should be the minimum heat demand that should be delivered at the end of my investment period to the buildings. So, for example, it could be 3 gigawatt hour or 5 gigawatt hours. Then, for filtering out irrelevant pixels or hectares, you should provide one value. So if I give here 20, it means that any pixels having less than 20 megawatt hour demand should be excluded from the analysis, and then the calculation starts. So this parameter is relevant when I have a huge area. I get a huge area for my analysis, and I think it makes sense that I refine obtained region a little bit so I can increase this parameter. Other than that, if I have like maxi approach and I want to get maximum extension of or possible district heating area, then I stick to this 20 megawatt hour. There is one parameter, district heating grid cost ceiling, and this is a value which should not be exceeded when I have a coherent area. So let's say I have multiple coherent areas. In each one of them, the grid cost that I have should not exceed this value. So this is basically calculated by calculation module. So the grid cost within the coherent areas, the average grid cost within coherent areas is calculated and compared with this number. If it is below 50 in this case, then it's a coherent area that I will keep in the result. If it's beyond above that, then it is not a coherent area and it should be refined further. I need to provide depreciation period. I need to provide a interest rate for the economic analysis. And then here is two optional parameters that I have to limit the annual expansion of district heating grids. So if I want to use them, then I need to modify these two parameters, and basically I tell how much am I allowed to expand every year. So I can give, instead of 10 to the power of 8, I can give like 10 kilometer per year, or 5 kilometer, or 1 kilometer a year. But another important input parameter is existing trench length. And if I want to use the functionality, then I need to provide both parameters. It's not possible that I just provide, I am interested in expansion of 2 kilometers every year, but I don't know how much trench length exists currently. Otherwise, the calculation module cannot calculate correctly. And the last parameters are for construction cost. So the default values that we have provided are coming from Synergies project. It's another European project, but the default data coming from them is from the year 2018. Still a good starting point for the analysis, but are a little bit low. In that sense, you may want to provide your own values, or you have better data and you know that it's cheaper or more expensive in your area, and you have the option to provide your own values. Here I have provided the values for my analysis for the case of Offenbach or region around it. Maybe it's still a valid number, you can use it. And I am going to use these values instead of the default values. Once you run the calculation module, you get set of indicators. You have the option to export them. You have to do it in order to use scenario assessment tool. And also there are a set of output layers generated by calculation module. For that, you need to go to the layer tab under the calculation modules. You can download also the generated layers. Before I jump into the exercise, I show a demo of the calculation module. Just need to go back to the platform. I have selected the region, still Offenbach. For this calculation module, you need two layers, current and future. Since we are calculating over a period of time, so either you use default layers on the platform, or if you already have generated layers as Marcus presented, or you have your own data sets, then you need to log into your user account. Then let's navigate to Offenbach. All right, I grab cloud tool level and select. And as soon as I select, I see that I have values for Offenbach. So let's go to the calculation module. It's the second calculation module under district heating and cooling. So as I mentioned, you have the option to pick here the default values. I select these ones, for example. Then you have the option to say you are interested in calculating from 2025 to 2045, for example. What is your current state? Which level you are interested to reach? What should be the minimum heat demand supplied to the potential district heating areas at the end of the investment period? What is the minimum heat demand in each pixels? What is your threshold level? This is basically a important input parameter for this calculation module. As Max previously presented, you have some orientation from the central heating supply. So when you open this Excel-based tool, district heat, the scenario assessment Excel-based tool, you first start with the central heat supply. You come up with some numbers, let's say 150 euro per megawatt hour for the central heat supply. And when you want to run the analysis for district heating, so basically the cost composed of grid cost or heat distribution cost plus generation cost. And in order to supply a region with district heating, basically you have the condition that district heating should be affordable, or at least a little bit cheaper or comparable with the central heat supply option. And in that sense, my overall cost may not exceed this 150 euro per megawatt hour, which is corresponding to the decentral heat supply. In that sense, you may go for values. If you don't have exact numbers in mind, you can maybe start with 50% heat distribution cost and 50% generation cost, and you play around with these numbers to get a feeling about the input parameters and also about the region you are studying. And with that, you can do the analysis further. So I don't change the depreciation time for the discount rate. Keep in mind that if you do an analysis comparing the central heat supply option with district heating, this discount rate should be constant over all your calculation. So if I take here, for example, 4%, it should remain in further steps also 4%. I do not want to limit the expansion, so I do not change these parameters. In the basic inputs, you can provide your own values. If you want to provide your own values for construction cost, constant and coefficient, you should select no here, otherwise stick to yes. And finally, we come up with layers that should be used, current heat density and future heat density. If you want to use your own layers from the user account, you just need to pick the right one. If you don't want, you just stick to the default data and then you run the CM. So let's wait a few seconds until the calculation is being done. Right, calculation finished. So here I see in magenta the extent of the regions which have been fulfilling the provided conditions. So basically it's calculation on greenfield. And these regions fulfill the conditions that I have defined here. And there are a set of indicators here. I can see total demand in selected regions. In the base year, in the last year, it's the same because I used the same layer for base layer and also for the last year. I see the total district heating potential again in the base year and in the last year. what is the absolute grid cost in million euros, what is the specific grid cost in euro per megawatt hour, also divided into distribution and service pipes, as well as the specific cost in euro per meter for distribution and service pipes, and finally the trench length for distribution and service pipes. And I have only one large coherent area. I export the indicators because I need this to transfer to my scenario assessment tool. And if you are interested in extra files, you can also export them. There are some additional files in it. There is also one output layer generated, and you can also download this one. And let's see, what do we have here? So basically, this is my indicators. It's the same as the ones you see here. There is still two other zip files. One is like shapefile for the extent of these regions. If you want to work with it in a independent of the platform, you can use this shapefile or Joe package file. It provides these magenta regions, and also some additional CSV file, which provides the attribute table of shapefile or Joe package file. But for our analysis, it's sufficient to have this indicator file, and you need to transfer these inputs and outputs to your scenario assessment calculation, scenario assessment Excel file. So I open scenario assessment file, I navigate to district heating economic assessment. Let's start with editing it. All right. What I need to do is just pick the values from the input parameter. I just copy them, Control C, and come here and paste the values directly here. So as you can see, it fits exactly to what I have. For comparison, I can also check with default value if there is a mismatch, so everything looks fine. And the next step is transferring the output ones. As you can see, it's starting with total demand in selected region. So I come from here, select the outputs, make a copy of them, and transfer it to the scenario assessment. As you can see here, I can run multiple times to get a feeling about the results, about the inputs and outputs here. So here we have up to 18 CM runs, calculation module runs considered. But for further analysis, for overall comparison between district heating and decentral heat supply, then we will need to select some of these scenarios. Therefore, we should select from this drop-down menu. So as soon as I'm here, I can pick the corresponding CM run. So that would be my scenario one. And as soon as I pick this one, then I see how much linear heat density do I have, and also what are the heat losses in the system based on values that I have provided, and also what is the district heating demand, including the grid losses. And this will be used further for district heating supply calculation modules, which will be introduced later. All right, that's the first run my suggestion is that you do multiple calculations so that you get a feeling about the inputs and outputs, how they have an impact on the analysis that I have. With this, let's go to the exercise that we have provided. It's about feasibility of district heating grids. So search about the current district heating market share in a district heating area of Offenbach am Main, as well as expected realistic future market share. So you may decide also for other regions, but then you need to adapt probably these two constant files, construction cost files, construction cost parameters, but they are provided for case of Offenbach, so you can use them if you calculate for Offenbach. So justify why a higher or lower future district heating market share should be solved. And also, what is the impact? So if I target higher market share, how the potential changes, or what happens if I have lower demand in future, and so on. Also search for other output parameters and explain why you think your chosen values are plausible. Make sensitivity analysis. So we had like these 18 different CMs run. You can provide them into the scenario assessment file and compare the final results. The procedure is similar to a demo that I had. So you finally need to identify 4 scenarios for your assessment, and also you run the calculation modules, you export the indicators as a CSV file, and then transfer the values to the scenario assessment Excel tool. And also it's good to have transfer of the layers for later analysis if you want to check them. Important note, before selecting a final set of input parameters, you should run the CM several times. As I said, it's a complex calculation module. You should get a feeling on impact of different parameters. And also keep in mind that you should keep the interest rate constant over your analysis. So if you have calculated for the central heat supply with, I don't know, 4%, then it's good to use the same interest rate here and also in the next calculation. All right, with that, I move on to the next calculation module, which...
Not sure, Mustafa, just to announce, yeah, we don't have a lot of time left anymore. Yeah, just...
Thanks. The next calculation module is about district heating temperature levels. Basically, what we saw in the previous calculation module was that for a predefined temperature level, it calculates the district heating. So CM district heating potential economic assessment, which I previously mentioned, it uses this interpolation analysis or procedure for identifying district heating potentials. And also there is a assumption behind it. So it considers a fixed supply and return temperature of 9060 because that was the values in interpolation or in the grid system which were used for interpolation. And also it uses a continuous pipe diameter ranges. So the idea is here, what happens if I have different set of temperature levels in my grid? So if I have like higher delta T, lower delta T, completely lower temperature levels, and so on, and what is the impact of considering this discrete set of pipe dimensions instead of having a continuous pipe diameter? And finally, check the impact on the CapEx and OpEx of the grid system. So the idea here is that going from the economic assessment calculation module and identified district heating areas, if I have the certain regions identified by the economic assessment module, what would be the impact if I have now a new set of temperature levels? And that's the purpose of this calculation module. I go to the platform to show how it works. So I go again to the layer, to the calculation module, sorry. And that's the third calculation module in the list. Basically, I can repeat the calculation similar to the economic assessment. As you can see here, many parameters have overlap with economic assessment, so they do not change. I think I gave one here. 74. So additional input parameters are supply temperature. So the default one was 90-60. Here I have given 80-45. You need to provide full load hours. That's relevant for the size of pipes. You still have the option to limit the expansion or providing the construction cost coefficients. The electricity price is relevant for OPEX. You need also to provide fuel price, maintenance, share for, again, comparisons if you want. If you don't want to change this, then put it 0. You have the option to adapt the pump efficiency and hydraulic and electric pump efficiencies and heat generation efficiencies. And the input layers are similar to the economic assessment calculation module. Once you run the CM, basically you should get similar to economic assessment, a layer here, but on top a comparison of CapEx and OPEX. So let's wait for a second. Now I have the result here. So as I said, if you provide a similar set of input parameters, you get the same regions. But on top of the previous indicators or main indicators, you get some additional indicators like what is the heat distribution cost for user-defined supply and return temperature. In our case was 80 and 45. Heat distribution cost, and also the O&M cost for user-defined supply and compared with the standard case. So as you can see here, with the new lower temperature levels, I have a little bit lower cost, CapEx cost, and also O&M cost decrease, I would say comparably higher than the primary one, the CapEx one. And you have again the option to export indicators and extra files. For this, we still have an exercise, but you don't need to transfer them to the scenario assessment because it's an advanced calculation module. We will not consider it in our scenario assessment. So use one of your main scenarios from previous exercise from economic assessment. Pay attention to additional input parameters like electricity price or efficiency levels. Try a new set of supply and return temperature with a delta T of 30, 30, below 30 and above 30, because our original delta T or temperature levels were 90, 60, 30 degrees C. Therefore, it's good to have a comparison. What would be the impact on CapEx and OPEX if I have the same delta T but different temperature levels, or below 30 or above 30? That's the whole idea, and try to understand what is the impact on the CapEx and OPEX. So procedure is same. Follow the the steps I showed just now and perform the calculation and export the indicators as a CSV files. If you run 3 times, and you will have 3 CSV files, and you can put the values beside each other and compare them. That's it basically for this one. With that, I give it back to you. I hope I did not exceed my time so much.
No, it's good. 5 minutes. That's totally fine. Thanks a lot, Mustafa. And I think it was quite a lot to explain, so it's anyway a challenge to keep in that time. Thanks a lot.
Okay.
Yeah, as we announced, always you have the option to put your questions in the chat if you have, but it's also clear that questions arise while doing. So yeah. With that, I give over to you, Ali. Thanks for being here today. Looking forward to your input.
Thanks, Marcus. So let's start the presentation mode. Yeah. So until now, most of presented the tools, the calculation modules we have for the district heating grid side. So how to distribute the heat and how to define the district heating demand. Now I will talk about the CM, district heating supply, CM, which we look into the options of how to generate this heat that we would like to provide with the grid. So giving a brief overview of the district heating supply CM. So what we do in this module is that we basically have an optimization module that minimizes the total cost of district heating generation. And mainly we can put these cost components into 4 categories. So we have the capital expenditures, the investment cost of the district heating supply technologies. We have the operational costs, we have the fuel cost, and then we have some related emission costs. And on the other hand, we have the option to have some cogeneration plants. So from these cogeneration plants, CHPs, we also produce electricity and sell this. We assume that all of them are sold. So you also have some revenues, and this is a negative cost for the model. So in this model, we have 2 main mode of operation. One is dispatch mode, only dispatch mode, and then we also have an investment and dispatch mode. So what happens in the first option in the dispatch mode is that you give the installed capacities of the district heating supply technologies, and then the model only optimizes the dispatch. So we only make an operational optimization, and we only use the capacities that are available. So the investment is not considered, the capacities will not be changed. But if you choose the second option, the investment and dispatch, here we have on top of the dispatch optimization and investment optimization. So you can still give your existing district heating capacities, installed capacities, or you can assume a completely new district heating system. So from the scratch, nothing is there, and then the model decides what's the installed. So you have these 2 options mainly to run with the model. The main inputs, we have some hourly profiles. You don't need to give any of these profiles, such as load profiles or electricity price profiles or some temperature profiles we use. On the other hand, we also have some techno-economic parameters used for these technologies. And we use this previously mentioned input generator Excel tool, which I will come in a minute and explain in detail. The main outputs of the model is that we have the cost of district heating supply and the breakdown of this cost. Then we have the supply mix, so which technologies are used to which extent. And then we have emissions. Of course, we have more detailed results, but these are the main results you will be receiving from the model. Also, one remark that this model works for a 1-year horizon. So we have an hourly calculation, but for a single year. So in this e-learning session, you can think of this as a target year. So we are modeling for the future year 2040, let's say. That's our decarbonization target. And then that will be the year that we are giving the parameters. So all the costs, everything should be for that year we are considering. And again, before going into detail of the model, I would like to also briefly mention what the model is capable and what it is not capable of. So the CM in the platform can use several technologies. One is cogeneration plants, CHP plants. By default, it's a wood pellet powered CHP plant, but you also have the option to change the energy carrier here. But the default cost parameters we give are for these default technologies, because with different type of energy carriers, you might have some differences also in the cost, for instance, for the investment cost. We have a waste incineration plant. It's also a cogeneration plant. Then we have boilers. By default, it's a biogas boiler in the platform, but again, you have the option to change the energy carrier. We have one large air source heat pump. This is the only large-scale heat pump we have within the model. And this one is sensitive to the temperature levels. So you will see later that we have some parameters for the grid temperatures, and those temperatures affect the COP of this heat pump. Then we have also the solar thermal, and finally we have direct use of waste heat. And what is not covered within the model, but these are also covered in the standalone module I will show later. You have this extended module as a standalone module that you can go to the GitHub code and download and run on your own, but this is not integrated in the platform. So this is more an advanced level. So the model you see in the platform cannot work with waste heat with boosters, so with heat pumps. We don't have storage implemented now in the platform yet. We don't have a specific geothermal energy technology option. And yeah, there are other technologies that are available in the standalone module. Also, an overall remark that this model or this calculation model is not able to model energy or these thermal networks. So what we model is, you can think more conventional third generation or fourth generation district heating systems. So I will give a brief overview on the slides and then make a demo of how to run model. So basically we have created an input generator for you to make the life easier for you, because this model is very dependent on input parameters, and giving them one by one in the platform is time consuming. So you have this input generator sheet, it's shown in the screenshot, and basically you fill it in, and we also have some default data. You click on this generate CSV input file, then and CSV file is automatically saved into the same directory as this file. Then you go to the platform and then choose this import CSV options. So you click on browse and then import and then run the model. So basically this is how to run the model. And then you will get some results, indicators, and some charts. So in the indicator parts, you will have several indicators. Maybe I talk about them in the platform later, but you can also export them, and you should do it to copy paste some data into the scenario assessment tool. Then you have several charts. I mean, here you only see 3 of them: full load hours, levelized cost of heat, installed capacities. We have more in the platform. And again, you can click on export charts. And again, you should do so to use the scenario assessment tool. And you basically get the data behind these charts, not the chart itself, but the data used to plot these charts. And you can also create your own plots working with them. And finally, you also have the option to export some extra files. When you click on this, you will get a zip file with one PNG file, which have this figure you see on the screen now. And then you will also get an Excel file. These are not necessary for scenario assessment tool. These are just to give you some extra outputs to understand what is used with the model. So first chart here we give is a load duration curve. So basically what you see here in the load duration curve, maybe I open the laser pointer. So here you can see, for instance, for this run, the base load is the waste incineration plant. And for the medium load, the model decides to use the CHP, and then the excess heat direct use. And for the peak load, it uses the heat boiler. So basically, this is the heat generation for each hour, but we just order it based on the highest load to the lowest load. So, so that's basically it. And in the Excel file, you have in this extra output files, you have the hourly load profile that is used by the model. So you can check this also to have a better idea, because the input you give to the model is the annual heat demand, not the profile itself, but you can see the profile. You can see the electricity prices and the profile used in the model. So you can again check, and again in the model you only have you are only able to give the average electricity price, so that is fit to this profile. Maybe before going to the exercise, I will also show you a quick demo on how to use this. So basically, as Mustafa also did, I will go to Offenbach. So in this CM, you have different geographical resolutions. So you can even work with the not zero, so for a whole country. So if I click like this, it will choose the whole Germany. Of course, this is not realistic at all. So if you do that, you will assuming that the area you choose is supplied by a single district heating system, so that all the technologies available in the model can supply the whole area. So this is up to you. You can go to maybe higher levels, not a single city, but normally we work with municipalities so that it's realistic that you are running the model for a single district heating system. Then I go to the calculation modules, and here in the district heating and cooling, we have district heating supply. So here we have different levels of inputs. So coming from the most fundamental inputs that you definitely need to check, to some more optional inputs, still relevant, but not absolutely necessary, and then some advanced level inputs. Here, most important one, if you run the model on your own without any outputs from previous models, that you need to give a district heating demand here. If you don't give and run the model, you will basically get an error saying you that you need to provide a valid district heating demand. But as you can see, here we have many repetitive inputs. So like the thermal output capacity, the installed capacity for each technology, and the maximum capacity for each technology. And this is repeated for each technology. So it's not very quick to fill in here. That's why we come up with this input generator. So it's a macro file. Therefore, when you want to use this file, you need to come, or maybe I show it because probably you will have this issue. You need to go to the properties and click unblock here. Otherwise, you will get a security notice from Excel. So you cannot run the macro. So now I allowed it by clicking that option. Now I can come here. So what you have here is you have all the inputs that are used in the model, in the platform. So we have some color coding here, as explained in the introduction section. It's the same color coding. So basically the green ones are the default values we provide to you. If you click here on data sources, you see where did we find this data. So what is the data source for this default data? You can change them, of course, it's up to you. As I said, you can change, oh, sorry, I clicked already. You can change the energy carriers. The gray ones you should not change. You have some instructions here. And right now we've pre-filled this data for Offenbach. And here, maybe I briefly talk about some of the input parameters. So the most important ones are these blue ones. So you need to give the existing capacities, the installed capacities. You need to give, if you are using the investment mode, what is the maximum capacity. So if you give a value of 0 here, we assume that there is no limit. So the model can expand the capacity as much as it wants. And one trick, if you say, okay, I have a technology that I have no potential, for instance, I have no excessive potential, but when you run the model, it will anyways consider it. What you can do is here, you can give a very small value so that the model not use it, or you can come here in energy carrier prices, you can give extremely high value. So I give like €1,000,000 here so that this is not used. Otherwise, of course, model will consider it. So you can give a very, very small maximum installed capacity or a very high energy carrier price. So it's not optimal to use it. So overall, here you have all the technology-related data, the efficiencies, the lifetime, the energy carriers, the investment and operational costs, and the ramping costs for the cogeneration plants. Here you have the energy carrier prices and their emission factors. For electricity, here you have a note that this is an annual average electricity price. So it will be fit into the profile we have in the platform. Here you can switch between this dispatch only and investment and dispatch mode. Here you have the distributing demand. So this should ideally come from the previous module Mustafa presented. So when you run this economic assessment module, you have, maybe I can quickly show you. When you come here in the scenario assessment tool. So when Mustafa pastes his results in this part, you see the district heating demand, including grid losses. Of course, you need to assume what are the losses in percentage. So I copy this value and paste it here so that I am in line with that. And it's also important to use the same interest rate here. Then you can also define here the CO2 price, the grid temperatures, as I said. And then when you click generate CSV input file, a file will be generated in the same directory. Be careful that if you are running in OneDrive or some directories you have no permission to write, you can get an error. So it should be a local directory that you have permission to write a new file. So as you can see here, it is come here. So this name you can change. So for instance, I will call it scenario 1, because if you click that twice, it will overwrite the file. So it's better to change the name. And now I go to platform. And here you have the import CM inputs. And then I click choose file. And here I have my file. I click open, and then you need to click import. And you see this message, they are imported. So basically, if I click here, I'll see for the ones that I defined some installed capacities or maximum capacities, I see the results. So basically, all the inputs are imported, and I click run CM. So depending on how complex is the problem, it takes up to 1 minute to run the CM because it's an optimization problem, and it's not always has the same complexity. It defines how you define the problem. It depends how you define the problem. So now we will wait more or less 30 seconds, I would expect. Yeah, now we have our results. So basically, in the indicators part, you have the total levelized cost of heat. So this is the levelized cost of heat for the whole system. Please note that as I showed in the slides, the revenues from the electricity is a negative cost here. So this is not pure cost. The revenues have been subtracted. So you see the total annual cost. You see the annual revenues from the electricity, how much heat has been generated, how much electricity has been generated, the different cost components, the emissions, what the heat demand you use. This is an input. How much energy the fuel has been used, which heat load profile and electricity profiles are used from these NUTS regions, and what is the peak demand. So on the chart section, here you have some basic charts showing you your results. So the full load hours for different technologies, the installed capacities. So for the same technologies, you see different results. The levelized cost of heat for each technology, the investment cost, operational cost, again, cost components, how much heat has been generated by each technology, how much electricity is generated, the revenues. So basically, you see all those results in a chart for all the technologies. And if I click on export extra files, so I save this file. So you get this zip file. And inside, as I mentioned before, you have one PNG file showing you the load duration curve. So in this specific case, since we already have a very big CHP plant, and from most of our results, I got just one result, which we have a very low district heating demand. So the most of the demand is covered by the waste incineration, and then you have some heat pump, CHP, and then peak boiler. And in the Excel file, in the extra outputs, opening in a second. As I showed before, you have the load profile used in the model. You have the electricity prices. You have the thermal generation mix by each technology. So basically, what you see here, what you see here is the same as this data, but this is just for each technology every hour, and this one is just sorted by the highest load to lowest load. Then finally, to use this with the scenario assessment tool, you need to export the indicators, and you need to export charts at the bottom. So now I go to the downloaded files. So I have the indicators and charts. So first, I will open the. These are okay. So now I will go to the scenario assessment file and switch to the district heating supply sheet. Okay, this is 3 fields. I will treat this for you. So I show you from the scratch how to use it. Same goes here. Sorry, quickly delete it. And this is it. Okay, so I basically open my indicators. And please note that you need to do this change of separators, this list separators, decimal separators. Otherwise, you don't see it in this format. And I basically copy the whole inputs section. So this is inputs. I come to my scenario assessment and paste it here. So I just paste the values. Yeah. So, and on the left, again, as Mustafa said, you have the default values, and these are the values you are used. Then I go to the output part and copy it. Here I paste the output. Again, you see with the default values. Then this part you see in the instructions, this should come from the figures. So the export charts part. So I open, this is the data we use for the charts. So basically this has been plotted. So I again copy the values until the last one. Oops, yeah, this is the last one. And I just paste them here and do nothing else. So I paste it here. As you can see, it fits with all the fields. And then here we have some, you can see some calculations for extra costs like electricity, the pumping cost, and the margin of the grid operator. And if you have some other costs, you can also fill them here if you have some other related cost. And basically, when I go to the district heating results, so most of the field his results for the economic assessment, and I filled for the district heating supply, you see a synthesis of both results. On the right, you see the values plotted here for the scenario 1. So we have the potential, district heating potential, the emissions, the investment cost, the cost components of district heating, the levelized cost of district heating, so on and so forth. And also we have some results for different building types. And here are the calculations. But the main idea of this is, of course, to have multiple scenarios and compare them. Before going to that, I will show you the exercise. Then Mustafa will briefly show you how it looks in the final version when we fill all the scenarios, because that's the main idea of the scenario assessment tool. So for the exercise here, we expect you to use the output from exercise 2. So as I did, you just need to copy the district heating demand and use it as an input for the district heating supply module. Here you see exactly where to find it, the district heating demand. Then you need to go to the input generator and then create your input CSV file, then import this into the platform, the module, and run this model, and then supplement your results into the scenario assessment file. So exactly as I did it. And we recommend that you try to discuss some of the results. For instance, which technologies are used, what are their costs, what are the energy carrier prices, and what are the specific reasons to limit certain technologies. So here it's very important to know what are the maximum capacities of each technology. Then we also recommend you to consider 2 to 4 different scenarios. This can be a mix of different technologies. So you can have more CHPs, more heat pump. In one case, you can consider using excess heat, or you can play around with energy carrier prices. So in case of a high electricity price, low electricity price, or different excess heat prices. So we recommend you to do this scenario development and then run the model, follow the same steps, and put them in the scenario assessment file and compare your results. So this is it for my presentation. I just realized I forgot to mention you that in the input generator, we also provide you this part where you can document your scenario assumptions. So it might be easier for you to follow them and document them. Yeah, that's it. And most of it, if you want to show, or if you have time for it, the final or the field version of the scenario assessment tool, you can share. And thanks
Great,
for your
thank you,
attention.
Ali. Thank you, Ali. Again, a rush through quite an intensive, yeah, and not straightforward tool for those who are not, for which district heating supply calculations are not daily business. Thanks a lot. Very good introduction. Mustafa, I think would be good if we show that now. Is that fine for you?
Yes, sure.
Great.
Sure. Of course, once I go quickly because we don't have much time. Once you provide the set of scenarios or data in both economic assessment and district heating supply, the charts will get updated and you can see what's going on. We have created here different indicators starting from district heating potential in the base year and also in the target year for different scenarios. Then CO2 emissions, investment cost as annuity. So you see different technologies here and also here euro per year. So it's in absolute term. And here you have the cost of generation in euro per megawatt hour. The overall levelized cost, so basically the grid cost as well as the generation cost altogether. So the afterward then full cost of district heating. This is coming for the single family house. You have the option to pick different building categories. They are basically the aim is here to have an idea of what would be the cost for those different building categories and get an idea for comparison. It's important to mention that the regions identified by district heating economic assessments are basically where the comparison of district heating and decentral heat supply is relevant. Whatever falling beyond these identified regions, of course, are not suitable for district heating, and there is no need to make a comparison. And you should go for decentral supply option for those regions. So the comparison being done here is mainly relevant for the regions that have been identified as potential district heating areas. Whenever we have costs which are cheaper than decentral heat supply option, then we will go for district heating. If the costs are higher, then maybe we should consider the decentral supply. Yeah, with that, I give it back to you, Markus.
Thank you. Thank you, Mustafa. Thank you, Ali. Good. I can imagine we're quite full already. Quite an intensive afternoon. And with that, we finish the heating part of the tool chain and we dive into the cooling part right now. For that, we have Adit here, who is the developer of the calculation module district cooling, and he will show it to you and us right now, together with an exercise as well. Adit, please.
Yep, thank you, Marcus. Hello, everyone. My name is Adit, and I work as a researcher at Technical University of Vienna. And now I'll be showing you insights on the district cooling calculation module. I hope you can see my screen. Yeah, so as Marcus said, now we move a bit away from heating and into the cooling side of things. But in general, I would still mention that this is still under a larger umbrella of heating and cooling planning. So here we still try to do some feasibility studies of network-based supply, but mostly from a cooling perspective. Yeah, so for today, I decided to start with a general, very basic description of what I'm talking about in terms of district cooling. So, of course, what is district cooling? It is a centralized cooling distribution where mostly chilled water is supplied through a network, through pipes to provide cold, or rather extract heat from buildings to meet certain comfort levels for occupants within the building. And why district cooling comes out to be a major question when we mostly talking about the feasibility of district cooling. So with global rising temperatures, we need to look for sustainable options for providing cooling. And district cooling provides one such opportunity, considering it has much higher efficiency due to centralized production rather than having individual chillers or split systems on a building. Also, the costs are considerably lower. The energy costs are lower, as well as the maintenance costs over a prolonged lifetime is much lower for district cooling units. And in terms of environmental impact, which is much lower compared to the use of refrigerants, as well as the impossibility of integration of renewables on a large scale. And also space saving is one important factor, considering the individual split units take up much space in individual buildings. This provides possibility of better space saving, as well as improved reliability in terms of more stable and optimized cooling supply, as well as supply security. How is it different from district heating? Of course, rather than providing heat, we are removing heat. But in more technical terms, the operating temperatures, the difference between the supply and return temperature, the delta T, is much lower in district cooling, which results in the use of the need for much larger pipes, which makes the economic assessment a bit different than for what is for heating. And also, we have the possibility of supplying from free cooling sources, which include mostly maybe from seawater, or also rivers or lakes, or any other water bodies, for instance, that could provide cooling as a free source. So to model all of these aspects and to see how feasible district cooling could look at different regions, we developed this calculation module called the district cooling calculation module. And what you can expect from the CM, firstly, the main approach here is to have a more techno-economic assessment of potential locations within a city that show feasibility for district cooling. So it is a generalized techno-economic approach, and based on we do this by assuming different costs associated to the network, the supply network, pumping costs for meeting certain demands, and also a simplified form of supply. And the outputs are expected as a first level screening rather than a detailed final feasibility study. So the idea here is that with a run, the user can assess different scenarios, see where exactly within a city district cooling could be feasible, and then based on identified areas, do a much more detailed, much more detailed feasibility study. And also with this calculation module, it provides the user with a possibility of simple way of comparing different scenarios to see under what conditions or when or where district cooling is feasible. With regards to the features, so the calculation modules works on 100 by 100 meter resolution. So on a pixel level, where it calculates cells where district cooling could be feasible. And for input layers from the default layers available in the citiwatts platform, it makes use of 3 different input layers: the space cooling need, the gross floor area total, and gross floor area non-residential. I'll come back to that. Also, and the idea then is, with the use of the gross floor areas, the 2 layers identify these so-called anchor points. So the idea is that a district cooling network, unlike heating, is mostly located around areas where there are consistent demand over the years, and mostly in the European context, this would refer to mostly non-residential buildings which require cooling all across the year. So what the calculation module mostly tries to do is identify these so-called anchor points and see if neighboring cells, or if there are even residential buildings around these cells, is it still feasible to provide cooling to these cells still in an economically feasible manner. And the calculation module works on a A.II region, mostly because district cooling is a local infrastructure and mainly planned only to meet local demands rather than working on a national level or regional level. And so regarding the analysis capabilities, there are different parameters that the user can tweak to see how this impacts feasibility. But two most that I would like to highlight here is the impact of electricity prices and how these anchors are defined. So with this regard, the expected outcomes from this calculation module are a GIS layer, which provides technical and economic estimates of different identified feasible locations. Also, for each of these locations, the costs associated to installation of the network, the pipe sizes, the grid lengths needed as such, and also a first level feasibility check on where these locations are. So on the right here, I have a very simplified schematic on what the calculation module is doing. So the idea is, here I have an example for the city of Vienna, where the idea is to identify different locations that could show feasibility for district cooling. And so, for instance, take one example here. So what the calculation model does is, as I mentioned, finds this point A, which is basically this anchor point, which shows the characteristic of these consistent demand points. So this could be, for instance, hospitals or the grocery stores or office buildings also, and then to see and then identify the cells around these anchor points and see if it is actually feasible to provide cooling in these regions with this network-based supply. So, for example, in my example here, I just wanted to highlight that, for instance, here it was feasible to provide cooling in this region, but however, here for certain conditions of the anchor point definition, it was not feasible. So, particularly this area is a potential location where district cooling grid can be further analyzed, but here not. And just to give you an overview of how the calculation module actually works, here I tried to simplify the working of the calculation module. So for instance, here each dot represents the different raster cells within a city, where for each raster cell we calculate the costs for developing a district cooling grid. And based on these costs, and then also for each of these cells, we identify the cells that show, let's say, anchor-like properties. So based on that, we filter out certain cells. So we only have these cells which show these anchor-like properties. And then what we do is based on certain electricity prices, we calculate the costs for how much it would cost if you'd rather supply from an individual system rather than investing in district heating. And for this case, we have about represented here by the orange line, the costs of the individual system. And then the model basically emits out costs that are more expensive than supplying from individual systems. So these are our potential anchor points, or rather feasible anchors. And then and once these anchors are identified, the model then again goes back to the whole cluster of cells within this region. And let's say for taking one anchor point here, we try to then see which, maybe for example, these blue boxes are the anchors surrounding this particular neighbors surrounding this particular anchor, and then the model basically checks if it is still feasible to supply to these anchor points, staying within the limit of the individual supply. So all district cooling identified areas are areas where the grid costs for setting up a grid is cheaper than providing from an individual system. So that's the basic working of the calculation module. Yeah, with regards to the inputs, well, there are quite a few, but yeah, I've categorized this into 3 parts. So the first one are the general inputs. So as I mentioned earlier as well, one of the important input is the average electricity price, where default values are put in, but also the user can of course change this. So the electricity price on one hand calculates this so-called threshold for the individual supply. So the horizontal line that I showed in the previous graph, but also it kind of yeah, adapts this price for district cooling supply, considering that district cooling networks would benefit from an industrial tariff rather than having a electricity price paid by residential buildings, for example. And then we have another input parameter on the estimated cooling days. So this is basically the user is expected to enter the number of cooling days that is expected in a year for the selected region. We've taken average values for Europe, but also this can be entered by the user. So this basically is used to calculate the peak load for each cell, and then it helps to identify what inputs are needed. And then we have the COPs of the district and individual and district system. Here again, the main idea again here is for district cooling taking advantage of higher COPs. It could make district cooling more feasible rather than individual system. So that's what the model calculates. And we have some economic parameters, including the discount rate, the lifetime of the district cooling unit, and the individual units, and a bit of more on the advanced set of parameters. Also, the user is able to change the delta T. So by default, the provided delta T is 10 degrees. But in general, the district cooling networks could vary from, let's say, 9 to 15 degrees as well. But if the information is not available, I think still sticking to 10 degrees would make sense. Another important parameter here is the threshold of non-residential gross floor area. So here, basically what this does is helps, what this means 50% is that an anchor is qualified to be an anchor. Basically, if the non-residential floor area in the cell is 50% or more than the total gross floor area of the cell. So this helps to identify different anchor points. And of course, the user can change this if even cells with lower non-residential areas are to be considered for district cooling. But of course, this would mean that there would be increase in the overall supply costs. And then we have costs for the individual units and district cooling units. So basically, these costs are then used for the calculation of the levelized cost of cooling. The default values are based on literature, but also if the user has specific or better local level values, then this can be changed. And then with regards to the input layers that I mentioned earlier, we have 3 different layers used as input, which then is used to calculate, to identify the potential areas. With regards to output, we have again, 2 different outputs. So one is actual spatial visualization of the identified locations for district cooling. So here again, I have an example of a test run made for Vienna, which shows different potential locations for district cooling. And of course, you can go to the layers tab, and for a user who has, let's say, more experience with the GIS-based applications, you can download this layer as a shapefile and use it for your for further calculations. But also, you can just click on the identify locations, and it gives you the module on the platform itself gives you more detailed information or technical as well as economic information on each of these identified locations. But on the right here, you see the indicators that are available on the platform. And then these are, again, more, rather than having for each of these individual locations, these are more on an average for the overall region under evaluation. So you start with the cooling demand, the percentage of demand covered, potential percentage of demand coverage by district cooling, how many clusters or potential locations are identified, which is 160 here, which is much higher. But again, district cooling networks in general are much smaller and scattered across cities rather than one big network seen in district heating. And also we have costs associated to investments. What would be the costs for the levelized cost of supply, as well as the overall costs for district cooling supply. I will just then go to the calculation module and make a few runs and show you how it works. So I will just zoom into Offenbach. Of course, you can search for it. And if you go to A.II region and select Offenbach and go to calculation modules, you can go to district cooling, the last one under district heating and cooling. So you come into the district cooling calculation module. You have, as I mentioned already, different input parameters that you can tweak. But let's go for the first run. I would just run with the default parameters to show you how the results look like. Again, I mean, since the calculation is being done on a hectare level, it largely depends on the time it takes to run. Okay, it's not working. Let me just refresh it just to be sure. As I was saying, the runtime depends on the location, how big is the area. So in general, for A.II regions, depends on 10 to 15 seconds, I would say, 15 or sometimes even up to 30 seconds. But let me just try once again. I hope it works here. So I go to A.II, Offenbach, and I go to calculation module, district cooling, run the default conditions. Yeah. So as you can see with the default conditions, the identified locations are quite small. It just identified two particular locations, which I would assume these are locations which are mostly around industrial locations, looking at the figures, not knowing the local topography. But also we see that about 0.56% of the demand can be covered by district cooling. But these are under default conditions. So now, for instance, if I change this to really high electricity prices, meaning that the cost of operation of individual systems would be much, much higher, and I run the CM, I would assume most likely the identified locations would improve greatly. Let's give it some time. Come on. Let's do it once again. Okay, this was something new. Let me give it to my here. Let's see if this works. Yeah. So I'm not sure what happened there, but maybe give it some time and it works mostly. So here what I did was change the electricity prices to a more realistic value. And also what I changed was the threshold on residential to, it was by default 50, so I changed to 30. So now what happened was it also considers pixels where the ratio of non-residential to total gross floor area is 30 or more. So even some residential buildings, which are most likely here, not considered in the previous run, is being considered for potential location, potential grid. And as such, the combination of electricity price change and the threshold change made the feasibility, made these areas more feasible. And of course, as I mentioned, you can click on these regions to identify different individual parameters, but also go to the layers tab to download the layer. And so for more, to make the scenario assessment more easier, we have formulated an Excel-based tool similar to what was shown for other calculation modules already. So you can export the parameters, which I should have here already, which would look something like this. And so as a user, you can just copy these values and bring it to what we have here, the scenario comparison sheet. So I have already copied this here. So these were our input parameters, and these was the outputs generated from the calculation module. And it then allows you to compare different scenarios, what potential coverage can be seen from district cooling and what are the potential levelized cost of cooling. I have a sheet which I have partially filled here already. So I have made different runs of scenarios to see how different parameters influence the supply. And yeah, we can see that for Offenbach, I have scenarios that have very minimal coverage, going as high as over 60% coverage, of course, with corresponding costs. But in general, with tweaking different parameters, and you're able to assess different scenarios to see potentials for district cooling supply in your region. Yes, so that coming back to the PowerPoint presentation. So as I mentioned, the input layers that we take in are mostly default layers available on the platform. So I would also like to mention of another ongoing project, which called Cool Life, which is a life project, which is dedicated to having different options or measures, calculation modules available for specific cooling related assessments. And there we have developed different layers for cooling demand as well, forecasting different scenarios of passive measure, upticks, and active cooling supply developments, where you have different raster layers also available for different projected cooling demands. So, so I have provided the links to these raster layers, and as a user, you could download these layers and upload it into your profile in citiwatts, and then use these layers to assess district cooling so you can better analyze let's say how district cooling potential would look like in the future. And also there are other dedicated cooling related calculation modules available within Cool Life, which could be used for further assessment of specific cooling related planning. Yes, having said that, I then come to my final slide, which is again on the exercise. To get yourself more familiar with the district cooling calculation module, you could try it for Offenbach as well, but also for your specific region of interest, we'd like you to run the calculation module and observe the impact of electricity price changes, how changing the price makes district cooling more feasible or less feasible in your region. And in addition, assess scenarios. So for instance, in a few years, you expect extreme increase in summer peaks or summer days. So how would you integrate this into the calculation module, and also analyze what impacts you would expect or you see in the model runs? And also the second one would be changing the anchor point definition, where you could change the threshold that I mentioned that I showed in my example, changing this threshold further and seeing how considering more or less number of residential buildings influences the coverage or the feasibility potential, and in turn what impacts it has on the costs for from district cooling supply. And of course, for every run, I think it is important to keep track of the individual costs. So how the individual costs, as in the individual supply costs, so how the electricity prices are influencing the individual supply costs, and in turn, what impact does this have on district cooling feasibility? And of course, if you are creating scenarios for, if you want to create scenarios for more let's say, detailed cooling planning, or actually development of cooling grids in a city, then the sensitivities of these parameters would be quite important. So this is also something that we would suggest you to look into. So having said that, that's all from me regarding the district cooling. And Marcus, I hand over to you again.
Thank you, Adit. Great. So we ran through the whole heating and cooling topic today. Quite a marathon, I would say. For the fast runners, this is also the time that could be reached. The very fast runners, 3 hours. Before we get, questions and answers, we still have time for that. I want to make 2 small notes before that. Just to show you that. On the one hand, you should have received an email today. Are we here? Looking like that, with also a hint to the recording on YouTube, and also this link to Google Classroom. And I'm not sure how many of you have followed this link already or not, but if you follow this link, you will reach the Google Classroom part, where all the materials that we've shown to you today, they are uploaded there. And so you need to sign in with your Google Konto or one of your Google Kontos and Google accounts, and then you are able to access it. So this is the starting page with the overview. And then if you go here, in German it's called Kursaufgaben, then you have the different slots, the different modules. And here, for example, for the module of last Friday, we have now here 2 materials for you. One is the presentation. You can simply download it as a PDF. And we also have the recording here, so you can directly see it. It's a link to the YouTube upload. Now for the session today, it's 2 citiwatts heat planning, toolchain and district cooling. Here for now, you have the report template, this PowerPoint template that I have shown you in the beginning. And we are going to upload all the materials that we have shown to you right away now. And you will be able to access them and use them. So that as an important point. So we're not going to send that around via email, but you need to just log in to that classroom, and you find the link in the email. If any one of you did not receive this email, please come back to us, whether in this chat or send us an email, send the persons an email that you have registered with. Yes, and that's it. Basically, you will be able to, I come back to that slide, so that you have that in the view. Where are you? You're here. So we're at the end of module 2 today, a rough one, a long one. I hope you have learned something today in the afternoon. I think it will definitely need some time to digest it. If there are any questions right now, please put them. if the questions come. As you can see, there will be a Q&A on Thursday this week. At the moment, I don't see any further questions. I see Max popping up. Hi, Max. Hi, Mustafa. Yeah. Of course, we know it was quite something that we presented today. So it's clear that this needs some time to go into it. Yeah, as soon as you check out something, as you try something, please don't hesitate to come up with questions. There is also the option in the classroom to put questions, so you can also do that. And as I said, there will be further sessions, and you can also get in direct contact with us. Yeah, if there are no further questions, we're going to close that session today. Thank you very much. You will be able to have also the recording. I think it always needs a little bit time to be ready. The Teams recording, that's one thing. Second, we are also going to insert timestamps for the different exercises. So most probably latest tomorrow morning, there will be the recording also online, and you have the opportunity to watch back the different exercises, explanations. You see how we did it, so you don't have to recall all out of your minds.